So this presentation will be about what we're doing at FLUDIA. And the long title is a lightweight deep learning model trained and combine available datasets, and I hope we will make sense of that. So I won't read, but we'll tell you a little bit about FLUDIA. There's something about smart sensors, because we are a device manufacturer. There's something about exploring NILM, because we like the subject, so why not? There will be something about deep learning and also a few results. I think you will understand that it's interesting. I hope so. And a little bit about content and future work. So FLUDIA has been active since 2005, first as a service company, so we provided audits and monitoring mostly for companies and professional buildings. And then we are a product company, so we are manufacturing devices, measurement devices, and we like that our devices are used for data analytics. It's not always the case, but maybe more in the future. The market segment is smart buildings and smart homes, and you'll understand why, because we're doing products that are plug and play, and of course they make sense in smaller buildings where the energy bill is not that high, and so you don't want to send someone to install an expensive piece of hardware. And our clients are mostly energy efficiency integrators, people that are providing services, and they are finding solutions, like our sensors, to help provide a service to either companies or residentials. Okay, and now I will be accelerating a little bit. The team experience is a lot of field measurements in the past, and so a lot curve analysis, and the development and production of smart energy sensors. And we've been doing a few of them and selling a few of them. I would like to say that a lot of them are used for NILM, but I can't say it because it's not true. A lot of them are used for basic monitoring. It's a shame, but it will change. We will work on that. So I'm Marc. Okay, I'm calling myself facilitator at FLUDIA since the beginning, so I try to help the guys work better if they can. And I did my PhD. It was a hidden Markov models for NILM back in 1996. Okay, sorry for that. I didn't realize that I was an old lady, so it's a bit strange, but okay, let's make it disappear. And Shamim here is presenting with me. He had his PhD in 2018 on machine learning applied to non-destructive testing, and now he's a researcher at FLUDIA. So let me tell you just a little bit about FLUDIA. So we're designing smart sensors that are compatible with large deployments, compatible with all kinds of existing meters, and they are plug and play, so they can be self-installed. And I think that's a key point for deploying services. They are ready for data analytics in the sense that they can provide 1 minute load curve or even 10 seconds load curve, and that's something that is useful, obviously, for NILM. And also there's IoT combined with the sensors, and we use a lot of different protocols, but we like LoRa and LoRaWAN because of the distance we can cover with it. Okay, and also what we're saying is that we are exploring NILM. We don't sell too much, we are just interested in the subject, and we are doing research inside FLUDIA. So until 2018, that was more probabilistic, but something, okay, we built with our own hands. And in 2018, Shamim has been evaluating machine learning algorithms, classical ones, and now he's been working intensively on deep learning and deep neural networks. And also, 2019 was a turning point for us, and we tried to start working on what we call multi-fluid, so combining data coming from electricity consumption, gas consumption, water consumption. And now Shamim will tell you a little bit more about the research.
Good afternoon, everyone. Thanks, Marc, for describing almost all the things about me. So I will briefly describe deep learning approach that we are developing at FLUDIA right now. So almost a conventional approach we are trying, but just thinking about the real test cases that we will be facing in the future for large deployment. So in that case, the first step we are addressing is data processing, where we are very interested for individual appliances. So we can say that the appliances of interest in our case higher energy consumption appliances such as dishwasher, washing machine, dryer, cooker, and so on. So in this case, we are trying to get those individual appliances from various datasets, and we are very thankful to available datasets like UKDL, Refit, FLUDIA. FLUDIA means we have some our own datasets that we have collected from France. And we are very also optimistic for HES because it's a larger data sets. It contains 2-minute interval data. So each of these data sets are varying in terms of energy retrieval. So you can see I said that HES is for 2 minutes, UKDL is for 6 seconds, Refit for 8 seconds, and FLUDIA has also for 1 minute. So our main goal is to try all of these dataset in a same interval. So we process all these dataset for 1 minute interval because we have our own device which can collect 1 minute dataset. And after combining all these datasets, we are doing some feature engineering. So in that case, we have used one of the good feature engineering or sampling strategy. It is called sequence to point sampling. It was done 2008 in a paper like Sejong. And by doing this feature engineering, we are just converting those application of measurements into sequence to point sampling approach. Then finally, we train our model, and for this case, we are thinking about our future implementation in our very short device. Like we have our sensors, so we are looking for some solution which can have a very high efficient as well as it can be very lower weight size, because when we want to integrate our deep learning model, then we need to think of where we can put our models either in the cloud or in the device. So that's why this is the approach that we are looking. And I found some interesting paper from Google. It is MobileNet, and I applied this MobileNet to our application. MobileNet was actually created for image classification, and it is really lower weight convolutional network. And to be noted here, all this sampling approach and this MobileNet approach, machine learning, deep learning algorithm approach has been treated in our own application. So all these applications, all these approach are modified according to our requirement. So here I'm showing some of the data set that I have processed. You can see that we have quite a huge number of houses available for HES, UKDL, then Refit, and then I divided all those things in training, validation, and test sets. So quite interestingly, we can see that we have a very good amount of houses available in test set. So this is very interesting for us to evaluate our approach and also to evaluate the model, how it is performing. So now I can show some of the results of these approaches that we have done. In this figure, I'm trying to show the true versus predicted energy consumption after disaggregation. So that means the orange bars are showing actual energy curve for an appliance. Like here it is a washing machine, and the green bar is showing predicted energy consumption. And in the horizontal line, you are showing we are showing the house numbers different from different data sets, and the vertical line is showing energy consumption per day basis. So because each of these data set contains difference of duration of data measurement, so we just normalize it to show that energy consumption per day, how it is. So you can see that not all the houses consumption are same. So this is one of the interesting results, because you can see from one house to another energy consumption is different. And then we can see some of the I started to very worse result. Here you can see that the predicted washing machine energy consumption is little bit higher than the actual energy. So why it is like this? If we compare the result here, you can see that this blue curve is the actual aggregated curve, and the green is the predicted washing machine, and the orange is the actual washing machine. So this block of washing machine has been very accurately predicted, but this block is not predicted very well, because it is predicted as a washing machine for this reason and also this reason. The model thinks, okay, it is a washing machine, but actually it is not. So it is that's why it becomes a little bit complicated for the model. And here this is also, maybe this is the signature of a dishwasher, but at the end this this reason is showing some of the behavior of washing machine. That's why it is little bit complicated for the model, and that's why it is not showing very good performance. Okay, not too good actually that we are interested in. Then I would like to see for the very good one here. You can see that actual and predicted energy consumption is quite good for this one, and you can see that actual and predicted energy consumption are almost similar, but it can track accurately for the washing machine that is consumed. So you can see that aggregated curve is here is a little bit complicated, because lots of appliances are active in this period, but even though the model is well trained, so it can predict quite good here. In this result, I am showing cooker, estimation of cooker in to be pointed here. Cooker means we integrated oven, stove, and general cooker, and then the results are combined as a cooker in this case. So at the beginning we can see that how it is performing for HES data set, and it is quite good for energy estimation. But for the other case here, you can see that the actual cooker is higher than the predicted cooker. So this reason you can easily visualize. Actually, cooking system is a little bit complicated, because sometimes it is, not sometimes, almost all the times it is depending on the user behavior. Some user can use the cooking system only for a few minutes, and only a small amount of stoves can be used. So that's why it is a little bit complicated in this case. One of the difficulties of the next appliance is dryer. So because we don't have so much dryer signatures, that's why we cannot get yet now very good, but I think the accuracy is around 10 to 15%. So you can see there is some missing of a prediction, because this block is showing okay, this is not a dryer, but actually it is a dryer, so it is a little bit different, but this block it is predicting very well. In another case, which is from FLUDIA 3, then you can see that the energy is consuming and prediction is very good. And the very good one is dishwasher, in my opinion, and we get very good prediction accuracy for this case. I'm just running out of time, so I want to give it to Marc for the concluding Marc. Sorry if I take a little bit more time.
No problem. Since there are two of us, we have extra time now. That's not the way it works. Okay. So just I'll tell you a little bit about the content, but just I think this topic we know a little bit about it, but I think it's key. It's how the content, which kind of content, and it has to be something interactive. And I won't go into these details. We are trying to do content that is based on energy, power, and also popular times of use and time of use. But the key point is to find partners that are able to leverage this kind of result and create a real user experience, something that is great. Future work, just rapidly, very rapidly. We intend, of course, to improve on what we've been doing so far. We are also working on something that we call multi-fluid. It's trying to combine measurements from electricity, gas, and water in order to create more content or more accuracy on existing contents. And we're also working on a simulator because, like everyone else here, there's a lack of labeled data. There are not enough of them, and working on a simulator is a way to increase the size of the database. Okay, thank you.
Cool.